Way back at the start of the year, we looked at heating diagrams, or heating curve. This was a graph that looked at the energy put into a substance and the change in temperature that it experienced. We're going to look at that again real quick. And then we're going to look at another type of graph. So in this graph, let's grab some different colors here. We have three different sections where the line slopes upward. Those sections are specific phases. The top section is gas. The middle section is liquid. And the bottom section is a solid. As long as we are increasing or decreasing in temperature, we are very solidly in one phase or the other. However, in these flat parts of this line, our temperature doesn't change because all of our energy goes towards making this phase change. And when that happens, we have this flat line representing going this way. For solid to liquid, we get melting. And from liquid to solid, we get solidifying. Or freezing. You'll see me use either one interchangeably. Going from a liquid to a gas, we have vaporizing. And going from a gas to a liquid, we have condensing. So that shows us that if I've got solid here, liquid here, gas here, we've got these processes that allow us to undergo phase changes, going from one phase to another, from solid to liquid to a gas. But we also do have a phase change, taking us directly from solid to gas or gas to solid. From gas to a solid, this is deposition. That's easy to remember because it's when the solid deposits right out of the air. Going from a solid to a gas directly is called sublimation. Sublimation. Now, that one's easy to remember because it's the only one that isn't common and easy to remember. I'm being cute. But all joking aside, this shows us that this straight line idea of phase changes isn't really that close to reality. It's more like having a triangle. It's more like solid can move to a liquid, could become a gas, which could become a solid. And we can have the reverse order. I want each of you to take notes on this. Write out this triangle. Label each of these transitions in your notes. Make sure you've got a heating curve and label all of these parts of it. There's 1, 2, 3, 4, 5, 6, 7 parts that you should label. Now, what we're going to get into next is answering the question of, why does this happen? And why does this happen instead of these, or why do these happen instead of this one? Why would I go from a solid to a liquid? Why would I melt instead of sublimate? When would that occur? Well, the next thing we're going to look at is called a phase diagram. And this is going to be another graph. This is one that you should definitely draw out. This is going to compare pressure with temperature. It's going to look something like this. In each of these three sections, we are squarely in one phase. Here we have solid. Let's use our colors again. Here we have a liquid. and here we have gas. Now each of our phase changes could be represented by a change in temperature or a change in pressure. Let's say this is H2O. Let's say this is water. Pressure, atmospheric pressure would be right around here. So 1 atmospheric pressure would be right around here. As long as I stay at that atmospheric pressure, then changing my temperature is just going to the left and right on this graph. If I reach a certain temperature, this would be 0 degrees Celsius. If I increase my temperature, I would melt. So we'll say melting. If I'm going the other direction, I would be freezing. As a liquid, if I reach this temperature, which would be 100 degrees Celsius, continuing on, if I continue to increase in temperature, well, that's where I would be vaporizing. If I cool down from a gas to a liquid, crossing this line right here, I would be condensing. Okay. Now, if I lowered that pressure enough, if I lowered it down to here, there comes a point where a liquid cannot exist. At this point, if I continue to increase in temperature, then I would sublimate. And if I decrease in temperature, I would deposit. Now, each substance is going to have its own unique version of this graph with unique values and variables, but they're all going to have this same general shape. So if I were to draw out CO2, it would look very similar. I think it looks more like that. But all of these values would shift around. For CO2, atmospheric pressure is around here. Room temperature is around here. So at this point is where we normally encounter carbon dioxide, which we exhale. It's purely gas. But if I get it cold enough and I freeze it, well, then I would have solid CO2. So this would be solid CO2. The common name for that is dry ice. Dry ice converts directly into a gas at room temperature. So all of its energy will cause it to become a gas. It will sublimate. And if you pour water on it, it will do that so quickly that it causes this very white, willowy smoke coming off of it. But that is pure carbon dioxide. So different substances can have different points, different places where they transition. In fact, on pure iodine, which is a solid at room temperature, it's at air pressure, atmospheric pressure, it sits right around here. And so as iodine sublimates, it very slowly goes through just a tiny liquid phase and then turns to a gas. It's a very interesting substance to watch because it also is bright purple when it turns into a gas. So let's look at this, let's clear this up, and let's look at a couple more things. Because there are a few limits to all of this. So I've got that graph again. Let's go here. Notice this, I continue trailing off, or this, I stop abruptly. There is a solid point on a phase diagram where this curve stops. This is called the critical point. Beyond this temperature, beyond this pressure, past the solid, the fluid in this area, it's impossible to distinguish it between liquid and gas. It becomes what we call a supercritical fluid. Supercritical fluid. Scientifically speaking, liquids and gases are both classified as fluids in that they can easily flow. At this point, anywhere in this sector of the graph, we are unable to tell a difference between the gas and the liquid phase, and basically everything is kind of both. it has properties of both. It's a really crazy substance. The other point that we want to keep an eye on is this one right here. And this is called the triple point. The triple point is a temperature and a pressure where all three phases of a substance can coexist in perfect harmony, where solids are not trying to transition into liquids or gases. Gases are staying gases. They're not trying to transition at all. At this point for water, it's at a temperature of 0.01 degrees Celsius. At that point, you can have steam, liquid water, and ice, solid ice, all together in the same environment, and none of them will be changing into any other form. They'll all stay that way. So these 2 points you'll need to be able to identify on a phase diagram. You'll need to be able to identify that this section is a solid, this section is a liquid, and this section is a gas. You'll need to be able to identify if I change my temperature at any pressure, what are the phase changes I'm going to experience? And if I stay at a certain temperature and just change my pressure, what are the phase changes that I will experience? The next 2 pages in the workbook are going to be looking at phase diagrams. So go ahead and tackle those. You should have everything from this video to answer those questions. They should be very possible. And if you have any questions, just ask them below. Thank you.